Hello everyone, I'm Duyu from Harbin Institute of Technology. So I will present a work named as a Joint Segmentation and Classification Framework for Sentiment Analysis. So this work was partly done when Dongli and me were visiting Microsoft Research at Beijing, China. So in this work, we focus on the sentence-level sentiment classification task. So it's a simple and a fundamental task in the field of sentiment analysis. So given a sentence such as a tweet as the input, the output is to predict its sentiment polarity. So in this paper, we focus on the binary case. So the polarity of a tweet might be either a positive or negative. So let's look at the existing framework of the pipeline methods. So given a training data, so each sentence in the training data has the gold sentiment polarity, and they will first use some segmentation algorithm to generate the segmentation result. So for example, there is a simple sentence that is not bad in the training data, and suppose we use the simplest segmentation algorithm that split a sentence as a list of unigrams. And then they will use the segmentation results as the input and use a classification algorithm to determine the sentiment polarity of the sentence. So here we find that the framework of these pipeline methods are not effective enough. So the reason is that they suffered from the polarity inconsistency between a phrase and the words it contains. If they simply split a sentence as a list of unigrams, and they cannot handle that, the polarity of the not bad, the phrase not bad, is because the polarity of the phrase not bad is positive. It's different from the polarity of its component bad, whose polarity is negative. And also, such a pipeline method always suffer from the error propagation, because during training they will use the polarity label to update the classification algorithm, but they cannot update the segmentation algorithm. So based on this consideration, we introduce a joint framework. So the intuition is to use the polarity label to update the segmentation algorithm. And we think that the sentiment-specific segmentation algorithm will help us to obtain a higher sentiment polarity performance. So we built this joint model based on two observations. So on one hand, the segmentation is important for classification. So the reason is that the segmentation result is just the input for the following sentiment classification component. And on the other hand, classification is also important for segmentation. So this is because whether this is because the usefulness of a segmentation can be evaluated by whether we can use it to predict the correct sentiment polarity. So now I will give you the inference process of the joint framework, and followed by the training process of the joint model. So for example, this is this sentence that is not bad. We want to predict its sentiment polarity. So at first, we use a candidate generation model to predict, to produce a list of segmentation candidates. So this is the first model, the candidate generation model. And then we use a segmentation ranking model to assign a real-valued score to each segmentation. So a higher score means that the segmentation might be more useful to predict a correct sentiment polarity. And then we will only reserve the segmentations with top k highest scores. And then we use a sentiment classification model to predict the sentiment polarity of each segmentation. So finally, we use voting to get the final sentiment polarity of a sentence. So there are 3 models in this framework. So this is the end of the inference process. And now let's come to the training process. So also this simple example. In the training data, we have a sentence for example, in the training data, we have a sentence that is not bad and its gold sentiment polarity is positive. And in the first step, we use a candidate generation model to get a list of potentially reasonable segmentation result. And then we use a randomly initialized sentiment classification model to predict the polarity of each segmentation. And after that, we can compare between this gold polarity and the predicted polarity, and we find that some results are right and some results are wrong, and we can use this as the supervision to update a segmentation model. And then we use the newly updated segmentation ranking model to assign a real value score for each segmentation. And at last, we will use the segmentations with top k highest scores to update the sentiment classification model. So hopefully, I don't lose you, and you still remember that there are 3 models in this framework. So they are the candidate generation model, the segmentation ranking model, and the sentiment classification model. So now let's come to the details of this model one by one. So the first is the candidate generation model. So this model, the purpose of this model is to produce a list of potentially reasonable segmentations for each sentence. So in this work, we use a beam search approach. So it consists of 2 steps. In the first step, we learn a phrase table from a large corpora. So each item in the phrase table is a unigram, bigram, trigram, 4gram to 5gram. And then we use the phrase table to get the possible segmentations with beam search. So there is a constraint that each basic computational unit in a segmentation must be either a unigram or a phrase contained in the phrase table. So for step 1, we just use the word-to-vector kit to identify phrase. So the identify phrase is based on the occurrence frequency of unigrams and bigrams, and we can run many times over the corpora to get longer phrases containing more words. So now let's come to the second step, the beam search step. So suppose right now we have get a phrase table and it contains 3 n-grams is not, so it's at this part. So is not bad and not bad. And now we have a sentence that is not bad. And I will show you the beam search process. So for the first index, there's only one choice. That is to leave that as a unigram. So it's the only choice. And then we move to the next index. There are 2 choices. So the first one is to regard is as an in-value computational unit. And the second choice is to concatenate is with the previous unit. And here, the second choice is not acceptable because the bigram that is not contained in the phrase table. So now let's move on to the third index. So for word not, there are also two two choices. The first one is to regard not as an individual unit, and the second choice here the second choice is reasonable because the background is contained in the freeze table. And similarly, let's move to the last index. There are also two choices. So if we follow the first line, the second choice, this choice is reasonable because in the freeze table we have the background not bad. And if we follow the second line, it's also reasonable because the trigram is not bad, it's contained in the freeze table. So now I have finished the candidate generation model, so it's just a simple beam search approach. And now let's come to the second model. The segmentation ranking model is the most important part of this paper. So recall that given a segmentation X, and we want to assign a real valued score to indicate its usefulness for predicting a correct polarity label. For example, we have 3 segmentations derived from the source sentence that is not bad, and we want to assign a real valued score for each segmentation. So in this paper, we use a log linear function. We think it's a straightforward solution, and there is an inner product between a weight vector and the feature vector, and this is just our function. So for the feature part, it consists of 2 parts. So the first part is 4 manually designed features. So they're simple. For example, the first feature is the number of basic computational units in the segmentation candidate, and the last feature is the number of basic computational units composed of more than 2 words. And the second feature is embedding feature. So the freeze embedding is learned from skip gram, and we just use this simple average, max, and mean, and we use their concatenation as another feature vector. So we concatenate these 2 kinds of features as the segmentation feature. And now let's come to the training objective. So given a sentence, so also this example, that is not bad, and we know that its gold sentiment polarity is positive, and we can use the segmentation the candidate generation model to produce some segmentation candidates, and then we will use a randomly initialized model to assign a real valued score to each segmentation. And here we will go one step further to predict the sentiment polarity of each segmentation. And here we can find that some are correct and some are wrong. So here we name the hit candidates as the segmentation candidates, so which can be used to predict the correct polarity label. And our objective is to maximize the scores of the hit candidates. And based on this consideration, we design such a loss function. So I think it's straightforward, and we also add a so this is the regulator, and this is the training objective. So based on this training objective, we can train the segmentation model without using any segmentation level manually annotation. So now let's come to the third model, the sentiment classification model. So in this paper, we use a traditional supervised learning framework. So we have the, you can find that, we given a training data, and we will first map each sentence into the feature representation. In this paper, we use 2 kinds of features. Also, the first one is the embedding feature, and the second one is one of the state-of-the-art feature given by NRC Canada. So they also give a tutorial in yesterday. And after that, we can build a sentiment classifier with learning algorithms such as supported vector machine. And this is the details of the feature description of NRC Canada. And for the second feature, the freeze embedding feature is as same as the feature used in the segmentation ranking model. So now let's come to the experimental part. So we conduct polarity classification of tweets on the benchmark dataset from Semantic Evaluation 2013. So here we only do the binary classification. So we do not consider the neutral case. And the evaluation metric is macro F score. So this is the result. So you can find that this is the SVM, supported vector machine with back-off words. And this is the recursive autoencoder. This is the naive base SVM. And so you can find that their performance is comparable. And so these two are the strong baselines, and the NRC Canada's is the state-of-the-art system. So you can find that they perform quite good because of the powerful features. And the last bar is our system, so it's just slightly better than this state-of-the-art. So we also conduct some experiments to compare our joint model with several pipeline methods. So here we have two pipeline baselines. So the first one is so in the first pipeline method, we use the back-of word segmentation, and in the second pipeline baseline, we use we segment a sentence to the segmentation with the maximum phrases. So here the different cluster means that we use different kinds of features in the segmentation ranking model and the sentiment classification model. So we find that in all these feature sets, the joint model outperforms these pipeline methods. So now come to the conclusion. So we developed a joint model to learn sentiment-specific sentence segmenter for sentiment classification. And our method yields comparable performance with the state-of-the-art methods on Twitter sentiment classification. So thanks for listening.
Questions? Yep.
Hi. It was clear, I mean, easy to follow on your segmentation-based approach with this example you use. It wasn't bad. So there was an explicit negation marker for polarity reversion. So I would be interested in, I mean, I was wondering how this polarity could be catch when there isn't an explicit negation marker. I'm thinking, for instance, when irony is used, some figurative language is used. So maybe it would be interesting to, I don't know if you tested your sample on some cases also that implied where you know, some figurative language, irony, sarcasm was used, and how it worked.
I'm sorry. So, so do you mean So whether the joint model can handle the negation phenomena, or
yeah, it was. I mean, it was interesting to know if you tested your approach on samples where, you know, ironic, sarcastic, expression were used in order to see how well it worked in terms of the sentiment analysis.
Oh, I'm sorry, I do not quite understand your question well.
So you compare your approach with you know, some state-of-the-art approaches in order to see how it works in terms of the sentiment analysis, right?
Yes.
And so I was curious to know if how well it worked on cases where some, you know, sarcasm, irony was used, more difficult in order to detect, you know, the polarity reversion effect without an explicit negation marker.
Oh, so perhaps in this system, the NRC cannot in their system, they just design some features to handle the negation phenomena, and in our joint model, perhaps I think so if they just use the back-of-word segmentation, so not and bad are separated in their method, and they design the negation feature to capture such phenomenon. And in our joint method, so perhaps the not and bad can be recognized as a basic computational unit. So we extract features based on this unit. So perhaps negation is handled in this way in our method and their system.
Hi. So in your model, you are kind of doing hard decisions for the segmentation when you feed back the classification decision. So I was wondering how, like, it would be nice to have probably a kind of soft decision and probably a latent variable model instead of making these hard decisions. Like you are now just discarding the negative ones, right? Like the impossible ones, let's say, this is or something like that.
So you mean this?
Yeah, so I was just wondering, like, how about you just replace this part with a latent variable model?
Okay. So in fact, we use the negative one because I'm sorry to missing the details. So in the denominator, so the AI means that all the candidates, all candidates, and the HI means the hate candidates. So the hate candidates means that so the segmentation candidate that we can use to predict the correct sentiment polarity.
Yeah. So my point is probably you should not like exclude those that violate this constraint. Rather, you should probably take a posterior over this. Like you probably take a average, probabilistic average over this. You can, you know what I mean? Just like EM.
Oh, okay. So you mean
like
I lost
when you take the segmentation one. So you are now in this example you will probably discard the first example, right? This is not bad.
Yeah.
But you should, like in a latent variable model, you would probably take the probabilistic decision on that, right? Kind of marginalize over all the possibilities to estimate the parameter.
Oh, we use LBFGS.
Yeah, LBFGS, but in an EM fashion.
EM.
You know what I mean? So I'm just telling that replace probably this one with a probabilistic latent variable model.
Oh, perhaps, so in this figure, I think it's not the probabilistic model. No.
Yes.
Yeah, of course.
Yes. Never mind.
So I want to be a little bit provocative here. Why do you need segmentation in the first place? I mean, if you have the phrase table that you kind of, you know, the term, actually, this phrase table term is a little bit confusing because you know, I'm start thinking of machine translation phrase table, which is probably not what you mean here. It looks like this is just like a list of terms that you have extracted, right? These unigrams and bigrams and whatever. The question is, why don't you just take all of them? You just have a dictionary. You just take all of them. Why do you need to decide on a particular segmentation? You can just extract them. If some of them overlap, so what? I mean, this could be like a useful baseline. Did you try to evaluate that? Instead of, you know, trying to come up with a particular segmentation, you just extract everything that you know is known to be a phrase according to your collocations.
So, but I think it has the size of exponential towards the number of the words contained in a sentence.
No, it's not exponential. If you just look at bigrams are at most twice the number of words there. It's twice, it's not exponential.
It's twice. I think it's also exponential. I think it's also exponential because the I'm sorry.
Maybe we can take this offline in the interest of time. Okay. Let's thank the speaker again.